Hi, this is Tom Hepner, and I'm part of IBM's Spectrum Enablement team. I support Spectrum Protect, previously known as Tivoli Storage Manager. In this video, I'm going to show you how to use the Protect server instrumentation along with the Protect client instrumentation to find what component or device is slowing down a client backup. Throughout this video, I use the term backup, but these comments also relate to restore, archive, and retrieve. Let's start by reviewing potential bottlenecks that might slow down your backups. First of all, there's the Spectrum Protect client environment. Disk drives, old or just defective units, are always potential problems. Poor configuration in the file system or the disk subsystem, large cumbersome workloads, millions of small files, or a deep directory structure, slow software, production applications, and even the backup software itself. Next, the network. It might just be a slow link or misconfigured network hardware. Also, sometimes we see high latency due to long distance or congestion. And then there's the Protect server environment, with many of the same factors as on the client, plus the back-end storage devices. So let's go through a simple problem scenario and test backup to illustrate troubleshooting using server instrumentation. I know that this is a busy slide, but it's meant to be. It simulates what things look like when you start problem determination. For our scenario, let's say one of the servers of the function test team is doing a backup. The system administrator noticed that it's running very slowly. He first calls the network administrator to check the data path. Our net admin verifies the correct path and checks for dropped packets or errors in the network logs. He sees none, so he declares the network trouble-free. The backup is still running slowly. What will the system admin do next? Probably call the Spectrum Protect admin, and that's us. So we check the production server with the Ops Center and see that there is indeed a problem with that client. The machine hasn't been completing its backups. So let's simplify the picture, which is exactly what you need to do when troubleshooting a problem. Break it down into small steps. Try to test one thing at a time. Here's a basic troubleshooting procedure we could use. Client instrumentation. If we see a problem here, we would look at the client machine metrics, network metrics, server instrumentation, and if we see a problem here, server machine metrics. So today, I'll run a backup with both client and server instrumentation. Since I already covered the client instrumentation in a previous video, I won't go into that in much detail. Here we are on our Windows client machine. I'll open a command shell and change to the BA client directory. My test directory is there. Now I'll get ready to run a selected backup of my test directory I prepared with 13 gig of data with files of different sizes. Here's the backup command. dsmc selective test \, then -test flag equals instrument:\detail. But I won't hit enter yet. Now I'll move to the Linux server machine where the Protect server is running. I'll open the admin client. I also could have done this on the client machine by just typing dsm admc. Now the server instrumentation is different than the client instrumentation in that it captures all the threads for all processes running on the Protect server. It is started from the admin command line by simply typing instrument begin or instr b. Instantly, we see a message saying that the instrumentation started. I'll also mention here that I've configured my primary disk pool with just 10 gigabytes of space and a next pool that has a device class of file. It has another 14 gig of space. Remember, our backup is going to be 13 gigabytes. Why did I do that? You'll see shortly. Okay, I'm back on my client machine, and I started the selective backup with the client instrumentation. We see the backup start. I'll skip to the end to save some time. And here we are. The backup is finished. Let's check to see if we got a report. I'll order the dir command by date, so we see our report at the bottom. And there it is. Notice the P864 in the report name. That's the process ID of the client backup. Now let's go back to the server and stop the server instrumentation. The command is instrument end, or instr e, and then file equals, and here I'll name it to match the client report. That way I have the two reports linked together via the client's process ID, in case I need to look at them again in the future. Let's take a look at both reports now. Here's the client report with the consumer thread at the very top. If you'll remember, a consumer thread is one that is responsible for transferring the backup data. Notice that this thread, 1204, took 265 seconds, and data verb was 214 seconds. Once again, data verb tracks the time after the client has sent a block of data to the server and is waiting for a response. In this case, after we do a little math, we notice that from the client's perspective, 80% of the backup was spent transferring the data across the network and ultimately writing it to a primary storage pool. While we're here, we can also note that about 10% of the time was spent in file I/O, reading the data from the client disk. But let's look closer here to see if that disk read may indicate a problem. Notice how many I/Os there were, 435,000. And how long did each I/O take? 0.1 milliseconds. That's fast. So the 25 seconds is the result of having a large number of I/Os, not bad or slow disk. There was also another 10% spent in the other category. This category tracks several operations during the backup, but it's non-specific, usually not very helpful in finding a bottleneck, except that it shows additional time spent by the client machine. Let's continue. Here's the area of the report that shows the backup command, client version, and client options. And finally, here's the output statistics. We see a reported network rate of 64,000 kilobytes per second and an aggregate rate of 52,000 kilobytes per second. Also note that the elapsed time was 4 minutes 25 seconds, or 265 seconds. Now let's take a look at the server instrumentation report. We see a report very different from the client's. This report includes performance-related threads for all processes running on the server while instrumentation is running. Let me explain how to read one of these threads. First, there's the thread ID. Then, the type of the thread. You'll find thread type descriptions in the optimization guide. See the link at the end of this video if you have trouble finding that document online. The thread's parent ID is listed next. This can be useful when you need to follow a chain of threads. Operation, count, total time, average time, minimum time, maximum time, instantaneous throughput, and total kilobytes. Each subsequent row has data for a specific operation of the thread. I think you'll find that most of these will be self-explanatory as we proceed through the analysis. At the bottom of each thread is a sum of the total time column. Now, the first thing we want to do in the report is find threads that were actually doing work. There are two primary ways to do this. First, look at the total KB column. This will have the number of KBs that were received, sent, read, or written. The second way to tell if a thread did any work is to compare the thread wait to the total time at the bottom. If the thread was waiting the whole time, how could it be doing any work? We can easily see that the first thread here did not do any work. So let's scan down until we find some threads that actually did something. And here we are, thread 51, a disk server thread. This type of thread reads and writes data for storage pools with a device class of disk. However, there are differences in thread types based on platform, so keep that in mind. You may have to check the optimization guide for specifics. Here's the name of the volume. The primary operation is disk write, and we wrote 219,000 kilobytes or 218 megabytes. Now remember, I mentioned that you look at the thread wait to see if the thread was doing any work. Well, disk server threads are different because these threads are alive as long as the volume is mounted. And because reads and writes occur in short bursts, the thread wait value takes up most of the time. So the definitive thing to look for is the number of bytes. And in this case, thread 51 did indeed do work. And if we look at the instantaneous throughput, we see that it wrote at almost 60 megasecond. Does that number ring a bell? That is very close to the network rate on the client. Let's keep that in mind. We can also see the number of IOs in the count column, the number of seconds that this thread actually spent writing, the average minimum and maximum IO in seconds. Please note that these IOs averaged 4 milliseconds. That's a good rate, another important piece of the puzzle. As we continue scanning down through the report, we see several very similar disk server threads that wrote to our primary disk volumes. And when we add up the amount of data that was written, it totals to approximately 7 gigabytes. Now there should be a thread to show the network reads, the thread that received the data. We're looking for a PS session thread. Here it is, number 199. This thread received 13.2 gigabytes of data from the network. Remember the backup? We see that that was exactly what the backup sent, so we can be fairly confident that this is the right PS session thread. Also note the rate, 128,000 kilobytes per second. Wow, that's pretty fast. Let's keep that in mind. Now let's continue on to see what else there is. Thread 205 looks interesting. First of all, it was writing to one of our next pool volumes. We also see that it wrote approximately 6 gigabytes at a rate of 64,000 kilobytes per second. Do you remember how much we wrote to the disk pool? 7 gigabytes. 7 plus 6 is 13. That matches our backup. And I configured this backup in order to show you how writing to a device class of file uses a different type of thread to write, an agent thread. But in both cases, we see the volume name and the disk write operation. So they're really not that different. And why did we write only 7 gigabytes to the disk pool that had 10 gigabytes of free space before the backup? The reason is that there were some very large files in the backup directory. And once the disk pool had filled up to 7 gig, there wasn't enough room to fit those large files, so it automatically moved to the next pool. I did this to illustrate how to follow a stream of backup data through a storage pool chain in the report. Moving on. Here's the thread summary section. This section confirms that we received 13.2 gigabytes and we wrote 13.2 gigabytes. It's helpful when only one operation is running on the server during an instrumentation. Things get a lot more complicated when there are several things running. I'll try to show that in a different video. When we continue to the bottom of the report, we see the DB2 section. Remember, the DB2 is Spectrum Protect's database that stores information about every backup object and tracks it through its life in the system. As we look at the DB2 metrics, we see a lot of low numbers, which is good. In fact, there's really nothing interesting here in this report. So I think I'll cover a more interesting scenario for this section in another video. Let's summarize what we've found. The client report showed file I/O taking 10% of the backup, and we determined that there was no indication that the disk reads were slow. DataVerb was 80% of the backup, and that tells us that the client was waiting for something outside of the client, network, or the Protect server system. Then there's the other category representing non-specific processing. However, if we add this other with file I/O, that combined 20% explains why the aggregate rate was slower than the network rate. So it is useful. At this point, I would conclude that the bottleneck is not in the client environment. Let's move to a summary of the server environment. The server report showed us that the disk writes averaged about 65 megasecond. The network transfer rate was 121 megasecond. That tells me that the disk writes to the storage pools were the bottleneck during our test backup. So what's next? I would go back to the system admin with this evidence and suggest that the disk subsystem be investigated, the one for the storage pools. And since that is outside of our backup software, I'll stop here. I hope you enjoyed learning more about Spectrum Protect performance and how to use the server instrumentation to find bottlenecks in your environment.